How do you listen to your digital music? Do you use slow, clunky apps like iTunes? Or do you stream your music online with Pandora, where you're limited to their music selection? Don't compromise anymore. Use RecoSonic. RecoSonic is a self-hosted music recommendation system that creates novel playlists based on a user's local music library. Current recommendation tools are either cloud-based services that require internet streaming like Pandora, Spotify, or Amazon Prime, or slow applications that have diminished performance on large datasets like iTunes. RecoSonic fills in the gap between these two sets of tools. It is a music discovery system optimized for large datasets of 500 gigabytes or more that runs on your own library on your own machine. So it's convenient and it's safe. By analyzing your music library, RecoSonic identifies your most listened to artists and recommends songs from similar artists who you will likely enjoy. Essentially, it lets you rediscover your music library. RecoSonic is written in Python 2.7, and it is built and integrated with the Subsonic open source music streaming app. Subsonic is a streaming app that installs on your local drive. It reads in and completely classifies your music library. Once classified, the Subsonic library is accessible using the RESTful API. This means you can access your artist's name, song name, music brain ID, the total play count per artist, and similar artists. In addition, RecoSonic makes use of the systemg Gremlin graph computing software developed by IBM. RecoSonic uses two main datasets, the Million Song dataset and the user's personal music library. The Million Song dataset is a free collection of audio features and metadata for 1,000,000 contemporary popular music tracks. This dataset was developed by Columbia University at Lab Rosa and also the company The Econist. Data is accessible using both SQLite databases or HDF5 file structures. The song's metadata provided by the dataset includes everything from the song's name to the artist name, similar artists, and general artist tags. In addition to the Million Song dataset, RecoSonic also uses the user's personal music library. For our experiment, we used our own personal music library. Our library was vast and had genres of all varying types, from everything to rock, hip-hop, classical, pop, and instrumental. Our music library was over 1 terabyte large. The next few sections show the general architecture of RecoSonic. There are 5 main portions of the RecoSonic software. A pre-processing section, a section where the similarity table between artists is created, a section where similarity ratios between artists are calculated, interface with systemg and Gremlin to find artist recommendation edges, and finally an output playlist. The demo will explain all these sections in much more detail. Although we were ultimately successful, we did have some challenges throughout this project. We had to determine whether we wanted to save our data to CSV files or to memory, and we also had issues using the MusicBrainz ID. Ultimately, we were able to overcome these issues, but these did cause problems temporarily. Here are our findings. When we imported our artist recommendation systems into systemg, we can see a very intricate web with many connections and recommendations. When we've tried to visualize the graph with a depth of 2 of only artists with over 100 edges, we can see the most recommended artists very easily. Finally, with systemg, we can easily and quickly get artist recommendations and then order them by similarity and visualize them. In conclusion, we successfully interfaced with Subsonic music streaming server to retrieve all artists, artist recommendation, as well as the most frequently played artists in our local library. We successfully interfaced with the Million Song dataset to retrieve artist recommendations and artist tags and term mining. We calculated artist similarity based on a number of shared tags and terms. We successfully interfaced with SystemG and Gremlin to view the artist recommendation map and queried the graph to find recommendation edges. We successfully created a playlist for each of the most frequently listened to artists, and then ultimately we realized that our system works very well, getting music which is actually very similar to our inputs. Now, there are a few different things we could do in the future to improve our product. We could give the user the option to create the playlist based off of songs either already in their library, like we're currently doing, or add totally new songs. Also, since the Subsonic local servers are accessible through the Android mobile app, we could make our playlist feature accessible on a mobile app. And also, we could develop a robust GUI framework to tie the tool together so that we're not running the program through the command line. And now, our demo.
Alright, so this is what the Subsonic interface looks like on the browser. I'm using Chrome browser, and the operating system's Ubuntu 16.04. Subsonic's installed. It's Subsonic, the latest version 6.0. This version of Subsonic is closed source. It's the first version that is closed source, but it still has the REST API just like the versions before it, and it's advanced, it's fast, very usable, and accessible from applications on iOS, Android, etc. All the music is stored on one external drive and one 2 terabyte internal drive, and very easy to navigate and play music. Very responsive interface. Adding music's very easy, etc. Alright, so we have done the implementation with Python, and it's we're using the IDE Lyclipse, which is a version of Eclipse, pre-installed with PyDev, very simple to use, and I'll go through some of the code, the major parts of the code here. So the very first step in running RecoSonic is to get the total list of artists. So what we do here, we are declaring where the Million Song subset or Million Song dataset path is. This is telling SQLite where the path is to open up the SQL files very easily, and a couple more functions that tell us how long things are taking. I have a function that cleans up some text that could mess up code and replace them with spaces. And I have a function that reads out the Subsonic credentials, so the server's address, the port, username and password are all saved in a text file, and then this reads it out. This is more secure to do this way than to upload on GitHub my personal server and username and password, etc. So, and this gives you more flexibility, easy to change right in the text file. And when you go to the main here, you see we start out opening writing a CSV file, artists.csv, and the fields are Subsonic artist ID, so each artist has a unique ID in Subsonic, and that's our main node ID that we use to identify them. This way we know this ID is guaranteed and it's given by Subsonic. It's going to be unique to the Subsonic instance. And besides that, we have the artist name, which is useful, we'll see later, the MusicBrainz ID, and the Million Song Dataset ID as well. So we write the header, and then we open up the SQLite track metadata .db file. So now there's the API call to the Subsonic server that gets all the artists, so a list of all artists loaded, and you see we read from the credentials list and fill in the address, port, username and password. We're using this version 1.14 of the API, that's the latest. We parse out the response to JSON and then iterate through it. It gives us an index, so each letter is separate, so we iterate through each letter, we read how many bands there are, and we initialize a couple of variables. Now for each artist, we go back into Subsonic and we query it for the artist info, and that's giving us some more information. It gives us the MusicBrainz ID. So we go through here, we try to get a MusicBrainz ID if it has it, and if not, we just leave it blank. That's fine. Very not critical, but it's there. Now if the MusicBrainz ID is not blank, then we query the SQLite database and we grab the artist ID from the songs that match the artist name. So this way now we're matching, we're finding the MSD ID, and we're using the artist name to do so, because we found that using the MusicBrainz ID to do that can get a little tricky. Subsonic sometimes mislabels the MusicBrainz ID, so we chose to use artist name to match, and it actually gave us a much more accurate data. So that's how we get the MSD ID. We grab them all, we parse out the data and clean it up, and then we append to a write. So it's a dictionary, so it's a list of dictionaries of the artist name, Subsonic artist ID, MusicBrainz ID, and MSD ID. And then we print out, how long everything took. Very simple. Alright, so now that we have the artist names, artist IDs, we can calculate the similarity between all of the recommended artists that we'll also find. So there's two big categories of recommendation that we get. Million Song Dataset has a recommended artists for a given artist function, so we can iterate through, find all the artists that we have, and get a list from Million Song Dataset. And then we also have a similar thing with Subsonic, so it gets its recommended artists through Last.fm internally, so it's all through the same RESTful API that Subsonic gives us. So once we get all the different recommendations from both of them, we kind of clean it up so we don't have duplicates, and we'll get to that soon. And then we calculate between all those edges and recommendations the actual similarity value, which will help us determine not just a blank, one value, but a more dynamic way to get very similar artists. So we start here. Again, we're coding in UTF-8. Same thing with the Million Song dataset location as before. Same thing with Subsonic credentials. A couple of functions to convert between a given MSD ID to a Subsonic ID, and vice versa. Here there's a function that reads the artist.csv file and returns a list of dictionaries containing all the data. So this way we're reading the CSV file once instead of reopening and closing every time that we're looking for this data. Originally, when we were figuring out Python and figuring out how to open CSVs, that's how we did it, and it took forever to calculate similarity, over an hour for one round. So this way everything's in memory, saves a ton of time, and I love dictionaries because you can just name things out and it gives you that data. I don't need it to be ordered. I don't need to remember which one's which position. It's great. This function, list of MSD IDs, it just gives back all the Subsonic IDs of artists that have an MSD ID. So anything that we found that's in the Million Song dataset will come back here, and that we'll see later how we use that. This function here, list of MSD ID text, takes in the list of MSD ID and turns it into one big text, appended text object that we can use for a SQL query that will also speed things up. We'll get to that also. Timer cleanup, again, we're getting rid of commas, which screws up CSV files. So unique pairs, this is how we're cleaning up the list of recommendations. So oftentimes you'll see one artist A recommending artist B that is similar, and then when you go and iterate through artist B, it'll recommend artist A back because they're similar. So this goes through and only keeps a single combination. So this is an undirected graph. This is an undirected edge, so we don't care which one recommended which. All I care is who are similar to the artist A. So it only keeps ones that are not already in the list. And similarly, combine clean pairs. So as we said, we have our lists of recommendations from Million Song dataset and a list from Subsonic. So between them, there are some edges that both of them share, so they both know that artist A recommends artist B that is similar. So I don't need both of them to recommend this to me. I just need to know once. So this goes through and starts out with list 1, which is generally longer, and then iterates through list 2, and what's not there gets appended. Now this is the fun part, where we calculate similarity between two artists. So the list 1 and 2 here that are given are actually lists of tags that artist A has, and a list of tags that artist B has. So we actually count how many shared tags they have and figure out how many total tags there are, unique tags. And if if this list is empty, if either of them is empty, and you see that here, we'll get a default similarity of 0.3. And we did this just by playing around with it, getting kind of a histogram, and seeing that 0.3 is a rough, good estimate of Subsonic's recommendation. It's not too high, not too low. And you can bump this up, like it says here, if you want Subsonic to be more influential on the recommendation. So it'll kind of float more to the top of the recommendations and play a bigger role. But for our testing and purposes, this worked. So we iterate through the items in the list, all the tags, and if they match, we bump up shared. That starts out as a 0, as a float 0.0, and then we calculate the similarity that gets returned equals that shared value over the total number of unique tags. So that will give you a number between 0 and 1. So now to the main function here, you see we open out the edges out file that we create, and again we have our field names, Subsonic Artist ID A and ID B, and their similarity. So that's our whole edge. Write the header, connect to the SQLite database of artist similarity, and that's where we get those edges from. We start out with the blank lists. We get the MSD ID and sub ID lists here. And then we iterate through each one. So we grab all the target and similar. So these are the edges from the million song data set, but we limit it to this query input text, and that's where we said we create a giant kind of text object that mushes together all of the MSD IDs that we have. So we don't want to keep recommendations of artists that aren't in Subsonic. That will be meaningless. It will try to get them and they won't be there. So so this limits it. It makes everything faster here. So we execute this query and we fetch it, and then we append all of the target um, artist A and B here. So that's all of the million song data set similarities, and then we move on. We clean out the edges. Like I said, we only get the unique pairs. That takes a little while, a couple minutes, and then we go in and convert all those million song dataset IDs to subsonic IDs, because eventually that's what we're going to use in System G and overall in the system. So after that's converted, that's pretty quick. We go in and ask Subsonic for its recommendations. So we get again the MSDID and sub-ID list, iterate through each one, and get the recommended artists. So then we iterate through that and save them, and clean again unique pairs, clean all of those recommendations out. And now we combine the clean pairs. That's what we went through before, and combine the two lists together. Now finally, we get to calculate similarity. So now we connect to the artist term database from Million Song Dataset, and that gives us all the terms, tags for each artist. So we grab all of our combinations and iterate through them, and for each one we query the database and we do a union. So there's actually two tables in that database. One is the artist term, and then the other is artist MB tag, so music brains tags. So I don't really care. The more terms and tags there are, the better. So I union them together to get as many terms as we can get. So we get these for artist 1 and artist 2, and then we throw that into calculate similarity and calculate the similarity between them. And very simply, now we create our write object and append to it. We write a row in the CSV file, and that's it. We close the connection to the database. Alright, so now that we have the artists and the similarities, we can upload that into System G, and I've already done so. So we can see here's the system, and it very easily takes in the two CSV files. So if I click here, you see it loads RecoSonic. Give it a little sec. It's over 44,000 edges, so it has to go through each one and determine where our center is and where to start the visualization. So it always takes a little while at first. And here we go. And we can map the label to the artist name, which gives it a little bit easier way to read it. And you see there's it's a big rat's nest, but still readable. System G beautifully arranges the nodes closer together as they are more um, internally connected, trying to keep more similar ones closer together. You don't quite get a let's say a sea of genres, metal here, rock there, and rap here, but it's still artists are interesting in that way where when we're reading tags instead of just a plain genre, it's more interesting, and it gives you a little bit more flexibility in terms of what is really similar to what. So that's what that looks like. So back to the code. Now I'll show you quickly to get top albums list, and we'll get to where we use that right afterwards. So when you query Subsonic for the most frequently played artists, it actually is most frequently played albums, and then we have to combine those albums into artists, because oftentimes when you like an artist, you listen to a bunch of their albums. So it's not straightforward enough to just grab the albums. We have to extract the artists from them. So first we get album list, and we use the same credentials as before, and we get the response, and then we combine these artists. And what we do here, we take the albums in and we iterate through each album, and we append to this combined artists list, and only keep adding the play counts for each album. So if I have 2 albums that I listen to from Metallica, one is 10 play counts, the other is another 10, then this will iterate through and give me Metallica with 20 play counts, and that's what we get back, combined artists. Then what we do afterwards is we resort it, because at first we do get a sorted list of albums, so most frequently played album is first, and then the second most frequently played album, etc., etc. But when you combine them, it kind of screws up the order, so we resort that, and we print it out just to show the top albums. Then when we use that to create playlists, we get that's our seed of data. So we find out what the user listens to the most, and then find other very similar artists that are not in that list. So we'll go through here. So this is the kind of the bread and butter Python script of creating the actual playlist. So we get our Subsonic credentials as always. Our extract time is the resorting, get recommended artists. So this will read the edges out. So this is how we've used the recommendations before. We just opened up the edges file and read out for each artist what are their recommended artists. But this next function does the same thing, but calls the system G graph database. So you get the same thing, but much faster, and very, very easily. And again, we already sort them by similarity. A couple more functions. So we get artist name, So we read out from the artist.csv, and so this kind of converts a subsonic ID and gets back an artist name, because the edges here only have the IDs and not names, and it's still useful to get the name. So this function here, clean IDs to artist IDs, takes the list of clean IDs, iterates through, and sends back a list of just the recommended artists. And this function here cleans recommendations. So it takes in a list of recommended IDs, a complete set of the seed data, which, like we said before, it's the top artists, most frequently played artists, and then we also have the recommended artist total, which we use later. But basically, this iterates through and kind of gives you back the full data of the recommended artists from the seed. Now here's where we get the top songs. So we take in an artist name, and that's where we use the artist name from the ID, and we query Subsonic to get the most popular, the top songs, based on Last.fm's scrobbling, to find each recommended artist's top songs, and we'll see later where that gets used. Very, very simple. This function, get albums, gives us a list of all the albums from Subsonic. I'll show you where we use that as well. And then get songs is it takes in album IDs and spits out all of the songs of that album. And now here's remove top songs. This takes in all the songs list from a particular artist and the top songs that we grab, and then only gives you songs that are not top songs. Also, we'll go through that later. This function creates a playlist name, and I opted for using a timestamp because you will know that it's unique every time, and you know exactly when it was created, so you can easily go to the latest one that was created or an old one, etc. And you could always go in and rename them later in Subsonic. It's very easy. This is a song list to text, joins all the song IDs, and these two functions actually make the playlist. So it takes in all the songs and then joins them together, so you get a big query that gets sent to Subsonic that creates the named playlist with all of those tracks. So now here's the fun part. We declare a default of 100 songs in a playlist. We found that to be very reasonable amount, and we take the seed in, which is our top albums, so most listened to albums, and we add together every artist's play count, and then we find out the total number of artist plays. So all of the top albums combined, how many plays we have. That way we know what is 80% of the total plays. And we only want to actually take in 80%, the top 80% most played artists, and then find their recommendations. There's too many one song here, one song there. This would be infinitely long, so 80% covers a vast majority. And it tells you how many artists actually amount to the 80% of the plays. And then we get that 80% of them. We find out how many subset plays there are, and we use that to calculate each artist's playlist portion. How many songs for each artist do we want to get that number of songs that represent them. We initialize some variables, and then we start. It's in a for loop of range 1, so it runs once. And we originally wanted or thought of running this twice, but found that this actually does the job really well once, so just left it just in case. So now for each seed, so the seed here is each top artist. We calculate the playlist portion, so how many songs do we expect to get recommended for this artist, and we initialize that seed artist with the leftover song num, so number of leftover songs. So it starts out at 0, and then basically if a certain artist, we can't find enough songs recommended to fill out this playlist portion, whatever's left over will come back in here, and it will be given to the next artist in the seed, which that's why we wanted to do it more than once originally, but with the leftover handoff, it seems to work really well once. So we do that. We get the system G recommended artist, so we query system G to find the seed's artist ID, the recommended artist for it. Then we clean those recommendations, right? We get rid of ones that that are already in our seed, and that's how we know that they're not usually played. And then we append them to the total list of artists. So then we take that list and we take just the top 3 recommended artists. This makes it very easy and simple to just, you get one seed artist, you get 3 recommended artists for each one. So now we divide it into those 3 artists. They each get a third of the playlist portion for that seed artist. So we get the top songs for that artist. Now if the size of that list is greater than the portion here, the divided by 3, then we can just grab a random sample of those top songs and then append them to the playlist. So if a certain artist has 10 top songs and all we need is 5, we can just grab randomly 5 songs out of these and append them. Now, if there's not enough top songs, then we grab all of the top songs if they're there, and then we get all the songs that that artist has in Subsonic, and then we figure out how many we get to grab from minus the number of top songs. So now if that length after we remove those top songs is greater than the portion, then there are enough total songs to grab from here. So now we go in and grab a sample, a random sample of all the songs that are left, and then append them. Now, if there's still not enough total songs and top songs to fill out that artist's portion, then we just grab them all and then give whatever's left to the leftover. So we iterate through each one and get all the songs through that methodology, and then finally, if the playlist that we have at the end, if that size is bigger than the original 100, then we'll grab a random sample out of that of 100 and finally actually make the playlist. And it's rather quick. It spits out something that looks like this, and you'll see it goes through, finds all the top artists and their counts, and you see a bunch of ones. Finally, top number of artists plays, it sums them up, finds that 27 artists span that 80%, and now we start to iterate through, and then the top artist gets 12 songs, and it found 3 bands, And Oceans, Fintroll, and Mythotin, and it actually tells you what that similarity is, so you see it's the top 3, and thankfully And Ocean has 6 top songs that we have, and it grabs 4 out of them, so 12 divided by 3, 4, so 4 songs each. And we go down this way, and we see that this previous artist, Sting, there's not enough songs that we found that are recommended, so we gave Flight of the Conchords 2 extra leftover songs that Sting couldn't fill out, and that's where we get Tenacious D, Weird Al, Dimitri Martin, and they very easily fill that out. And we finally go and we see that printed list of song IDs, and it tells us, confirms the size of the playlist, and eventually, and then when we look in Subsonic playlists, and there it is from today. I just ran this a couple of hours ago, and all the songs that we saw before are right there, and appropriately amount to the most listened to artists. So that's it.